So this will be a tutorial on hardness of approximation in NP, meaning it's hard to approximate solutions to NP hard problems. And there is also hardness of approximation in, you can call it W1. That's the topic of fixed parameter tractability. And then in P, that would be the topic of fine grained complexity. And there are going to be tutorials on these topics. Now, the hardness in NP, this is a rather long-running and rather successful project, at least for 35 years. So it's not that I can compress the whole thing in 1 hour. So this is more like a tutorial, and I will just essentially just throwing in a whole bunch of references. And of course, you can go and check out these references, surveys. Maybe if I have to recommend single most source of pointers, Ryan O'Donnell, he definitely taught the course maybe even multiple times. I'm sure he has many online lectures, lecture notes, even has a book on analysis of Boolean functions and so on. So that would be my single most recommendation. So this topic, hardness of approximation, I guess in NP, I mean you can view it from 3 different perspectives. Focus more on like results. You could focus on the underlying techniques, or you could try to fit everything in terms of some high-level framework. And we'll do all 3. So here are some results, arguably maybe the most prominent ones. So I will quickly go over these. So for 3-SAT, there is 7/8 plus epsilon hardness result, meaning given a satisfiable instances of 3-SAT, it's hard to find assignments which are 7/8 plus epsilon satisfying. Throughout, epsilon would denote arbitrarily small constant. And this is optimal because you can always do 7/8 by just taking a random assignment. For click on n vertex graphs, n to the n minus epsilon, which is again optimal because n is just trivial. Algorithmically. For set cover, we know there is a natural log of n approximation by greedy LP relaxation rounding, and you also have matching hardness result. So these are bona fide NP hardness results, like gold standard. There are more prominent problems for which we actually don't have these bona fide NP hardness results, but we can do things under conjectures such as this unique games conjecture. For example, we could do optimal 2 minus epsilon for vertex cover, optimal 0.878 plus epsilon for max cut, this being the ratio obtained by the Gomans-Williamson's max cut algorithm. There's a problem called max acyclic subgraph. Given a directed graph, you want to order it on a line so as to maximize the number of edges which go forward. So you can certainly do half algorithmically, just either take do arbitrary order and either take the edges forward or backward, right? So that's going to give you half, and it's hard to beat half. And there are many questions open. For example, the metric version of TSP, sparsest cut, which is cutting graph into 2 roughly equal parts so as to minimize the number of edges crossing between the 2 paths. There is a shortest vector problem in lattices. Specifically, to get a reduction for this problem, which is deterministic, that's still open. Or get factors which are polynomial in the size of the dimension. That's also open and great open problem. There are many. So the results, if I have to quote a few. The techniques, it's usually combination of combinatorics, coding theory, increasingly so as the decades went by, Boolean function analysis, and that ties in very nicely with geometry and especially isoperimetric type inequalities in geometry. And then everything which is specific to the context in which the problems arise. Right. So for example, if you want to do SVP, you would have to know the things about lattices, integer lattices, so on and so forth. So that's in terms of results and techniques. I think it's more helpful to view these results in terms of a framework. So I will write it here so that it always stays throughout the talk. Vast majorities, if not essentially all, results start with what's known as the PCP theorem, which I would call, the grandmother of all hardness results, because essentially everything flows from this. There are some, I can think of two quite interesting results, which can be done without assuming the PCP theorem. So I will quote one of them. From PCP theorem, one can show some results in a direct fashion, though I have to say I don't have an example here which is, I would consider most compelling. I might be missing out on something. On the other hand, vast majority of results, they would start from the PCP theorem. Then there is a step which is called parallel repetition. And which proves hardness of a problem called label cover. And this hardness result for label cover, I would call this mother of all hardness results, because essentially everything follows from this point onwards. Now, from this point onwards, you could have just a direct reductions from label cover, and there are quite a few of those. But I would think even more dominant theme is you take one more, add one more step in this thread called dictatorship testing. And then that leads to many compelling results. In particular, results for all what can be referred to as CSPs, constraint satisfaction problems. So 3-SAT being 3-SAT max cut, these being constraint satisfaction problems. So you can prove a whole bunch of these. Okay. And that's, I guess, a very high-level framework. And then you can add more stuff to this picture. So for example, I could say, what's this whole thing called unique games conjecture? So think of this as a stronger version of the hardness for label cover. But we don't know it for sure. So we only need, we are at this point, we can only conjecture that some stronger version of label cover is hard. And then once you assume this, this is going to lead to many more things, such as vertex cover, max cut, and so on. What else? There is a related theme, which is called integrality gaps. These can be thought of as hardness results, but for very specific family of concrete algorithms based on linear programming and semi-definite programming relaxations. And that also somehow ties into the whole thing. Okay. Yeah, so if you want to take, in some sense, very high-level view of what this area is, it's like the combination of all these three, and how all the results techniques and these frameworks, they sort of interrelate. And I hope to at least cover a little bit of everything in that last high-level framework. So let me quickly start by simply quoting one result, which is super nice, without even using PCP theorem. So this is hardness result for directed version of edge disjoint paths. So where you are given a directed graph, you are given directed graph and pairs, sourcing pairs, S1, T1, S2, T2 up to some S sub L, T sub L. And the question is to find directed paths from SIs to TIs, the corresponding TIs, which are all pairwise disjoint in terms of edges. Okay, and it's optimization problem. So find as many such paths between pairs as possible. Now, it turns out that the problem is NP-hard already for when the number of pairs is just 2. Okay? But this is not an easy reduction. I hope we appreciate that there are some plain old NP hardness reductions, such as, for example, TSP, which are actually quite difficult. So this one is, I think, similar, right? Just finding 2 disjoint paths between 2 pairs. This is NP-hard. But then turns out you can take this hardness result, or rather hard instance of this problem, and then use it as a gadget in a higher level reduction to show that this problem is very hard. Okay? So this basic hardness result is just used as a gadget in a higher level reduction. And then you can show that, so this is hard up to factor which is m to the half minus epsilon, where m is the number of edges of the graph. So this problem is really, really hard to approximate. And square root of m, there is also approximation algorithm, so this is tight. Okay? I mean, if you are sort of new to this area, I highly recommend just looking at this reduction. I could even draw a picture here. It's like this. You construct a graph, new graph like this, and each intersection point of this grid you replace by hard instance of this problem with two source sink pairs. And one source sink pair is connected vertically and the other one horizontally. And that's it. This is the reduction. Okay? But in any case, let's not delve too much on this. And this is by Guruswamy, Khanna, Rajaraman, Shefford, and Yanakakis. So let's jump to the foundational result, the grandmother of all results, the PCP theorem. So this was proved in early 90s in a sequence of 3 papers: Feige, Goldwasser, Lowa, Safra, Sagedi, Arora, Safra, Arora, Lund, Motwani, Sudan, Sagedi, and preceded by a very large influential body of work on program checking and interactive proofs. Now, as the name suggests, this refers to probabilistically checkable proofs theorem. So it has to do with program checking, proof checking, whatever that means if you are not familiar with this. But it also can be phrased as just as a hardness of approximation result. So for the purposes of this talk, I will just stick to the following statement. So it simply says that it's NP hard to distinguish whether a 3-sat instance phi has optimum 1. So optimum here would refer to what's the maximum fraction of clauses you can satisfy in a 3-sat formula, right? So optim equals 1 just means the formula is fully satisfiable. Versus the case where the optimum is strictly bounded away from 1 by a constant. So at most C, where C is, let's just say 0.99, doesn't matter so much, okay? But as long as it's a strict constant, strictly less than 1. And then that's the result, that's it. This is what is the PCP theorem. So this problem where a formula is either satisfiable or what you can call highly unsatisfiable, okay? Meaning any assignment, not that it fails on some clause, in fact it has to fail on constant fraction, 1% of the clauses, right? So this is referred to as gap 3-sat. So one way to state the theorem is that just gap 3-sat is NP hard, okay? Now, just to emphasize, so in other words, there is a reduction from 3-sat to gap 3-sat, right? And this reduction would map one formula to another formula, right? But with the property that if the original formula is satisfiable, the new one is also satisfiable. Whereas if the original formula is unsatisfiable, the new formula is highly unsatisfiable, okay? So that's just yet another way of saying the same thing. And this is the famous PCP theorem. So clearly, it already gives hardness of approximation result. When arguably, like a mild hardness of approximation result, that there is some threshold, in this case 0.99, beyond which it's hard to approximate. So as you would note, I'm being a bit sloppy. Sometimes I think of the hardness factor as some number less than 1, sometimes larger than 1. So I hope it's okay. However, the immense significance of this result is that before this theorem came, it was like being in the dark ages. For all you know, before this theorem, it could have been possible that 3-sat, vertex cover, all these problems, they could even be approximated up to arbitrary degree of accuracy, right? Meaning that 1 plus epsilon approximation where epsilon tends to 0, right? Right. However, once you know the PCP theorem, it follows, and this was already pointed out in a paper of Papadimitrov-Yannakakis, that once you have some mild hardness result for 3-sat, you automatically also have mild hardness result, what's called APX hardness result for all these problems. Okay. So now PCP theorem brought us out of the dark ages, and there was light. Now, what can you do just using directly the PCP theorem? So as we already said, we do get some mild hardness result for all these problems. So in particular, let me demonstrate how you could get pretty good results for clique. Okay, and there is a purpose to this to illustrate what's usually known as the FGLSS reduction. Okay, so it's a reduction from 3-sat to clique. 3-sat henceforth would implicitly mean gap 3-sat, right? It's either satisfiable or at most C-satisfiable. So you want to map a Boolean formula phi to a graph G, so that in graph G there is a gap in terms of the maximum clique size. Now the reduction is, at least in hindsight, it's or at least by now it's standard. So you look at the formula phi, call the variables x1 through xn, and let's say there are m clauses. From this you construct a graph as follows. There is one block of vertices for each clause. So this is block number 1, block number 2, and so on up to block number m. So there are m blocks. Each block has, in this case, exactly 7 vertices. So the blocks correspond to clauses. So let's say this clause is x or y or z, or x1 through xn, it doesn't matter. And let's say this block is x or maybe w or b, something like this. The main point being that they share a variable called x, right? Now, in each block, of course, there could be negations. The variable could be negations, but let's drop that. You can take care of it. So each block has 7 vertices, which simply correspond to all satisfying assignments to the clause. There are 7 assignments, right, which are satisfying. So let me group together these assignments into those which assign 0 to x and those which assign 1 to x. Now, x can be assigned 0, and then there are 3 possibilities, right? On the other hand, if x is assigned 1, then the values to y and z don't even matter. So there are 4 possibilities. So that's a total of 7 vertices. Similarly, on the other side, there are 3 assignments where x is 0 and 4 assignments where x is 1. Okay. And now I draw the edges between vertices, and the edges are simply going to represent consistency, meaning the value to x is the same in both the blocks. So it's really just amounts to having a complete clique here and complete clique between these 4 cross 4 vertices. That's it. So edges simply represent consistency. In particular, each block by itself is independent set. Okay? And then that's it. This is the reduction. Now it's clear that if the formula is fully satisfiable, then this implies that what's the size of the clique? I mean max clique. Okay? So there will be a clique of size m, because you just pick one vertex from each block which is the assignment to that clause under some global satisfying assignment, right? And everything is going to be consistent, all good. On the other hand, if this formula is only at most C satisfiable, then it's fairly easy to conclude that the maximum size clique will be of size at most C times M, right? Again, because if you pick one vertex from some of the blocks, they must all be consistent if it is to be a clique, which amounts to having some global assignment. And then you can satisfy only C fraction of the clauses, and you can only pick vertices from fraction C of the blocks. And that already gives you a mild 0.99 hardness result for clique. Okay? But there is something nice about clique, that you can amplify the hardness result for clique by simply taking graph products. Okay? So you can start with this graph G, which is obtained by this reduction, and then take the graph G to the K. This is the graph product. Let me not even define it, right? The vertices are just tuples of vertices, and you connect two tuples if there is an edge on every coordinate, right? And it's very easy to show that the size of the maximum clique is just multiplicative as you take the graph products. So in the graph G to the K, it is the case that either size of the clique is M to the K, or is at most C to the K, M to the K, right? Depending on which case you are in. And you can take K as large a constant as you want. It would still be a polynomial time reduction, and the gap would just become arbitrarily large constant, right? You could even take K to be log n being the size of the graph. Typically, in all these reductions, you can always assume that number of vertices and the number of edges, they are all linear in each other. So, so if you take K equals log n, you would even get a hardness factor which is a function of n. But then you want to express it as a function of the size of the graph, which also keeps blowing, right? So here you can only get hardness factor which is something like this, 2 to the log n to the 1 minus epsilon, where n is the size of the graph after the products, right? So this is fairly commonly referred to as almost polynomial factor. It's almost there, as a polynomial function of capital N. However, you can do something even nicer for the clique problem, that once you have this product graph, you can simply take a random induced subgraph of it of much smaller size. In fact, of size which is polynomial in the little n. So if you take random induced subgraph of size something like, let's say, little n to the 10, then turns out you actually preserve the hardness factor. You have to prove it with probabilistic calculations. It's no big deal. And now it's a much smaller subgraph. So if you express now the hardness factor as a size of the output graph, now it's actually n to the some little constant. Okay. Yeah. So this is just a demonstration that you could get n to the little constant hardness for clique just purely immediately from PCP theorem itself. Okay. Now, so I hope everything is clean and clear so far, but do feel free to interrupt. Now, of course, I mean, you always want to get optimal results, and eventually it does turn out to be the case, which in fact we already noted in terms of the main results, that in this theorem, PCP theorem, this constant C can in fact be taken as arbitrarily close to 7/8, right? And in the hardness result for clique, this can really be pushed to not n to the little constant, in fact n to the constant which is arbitrarily close to 1. Okay. But these results require building further and further on top of the PCP theorem. And that's the purpose of this thread. Start with PCP theorem, then parallel repetition, dictatorship test, and then you eventually get 7/8 plus epsilon for 3 sat and n to the 1 minus epsilon for clique, among many, many other results. All right? Okay, so I think we at least gave you examples of this, this, and this. Okay. Now let's see what this parallel repetition business is, the label cover, and we'll quickly see an example of direct reduction from label cover. 958, all right. So what's label cover? You start with 3 sat or gap 3 sat, which has variables and clauses. From this, you build an instance of label cover, which is it's a labeling problem. So you construct a bipartite graph whose left-hand side is all the variables of the 3 sat instance. The right-hand side is all the clauses of the 3 sat instance. Okay. And you connect a clause to the 3 variables which appear in that clause. So maybe the clause is xi or xj or xk, in which case you are going to connect it to the 3 vertices xi, xj, xk. So that's the bipartite graph. Now it's a labeling problem. So each variable is supposed to be labeled either 0 or 1. Which then simply amounts to assignment to the formula, to the variables, right? And each clause is supposed to be labeled by one of the 7 assignments which satisfy the clause, right? So the number of labels here is 7. You can think of them as just integers from 1 through 7, but they are really can also be interpreted as actual 7 assignments. In this case, it would be 0, 0, 1, da, 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 all the way up to 1, 1, 1. Right? Good. And that's it. That's the intention. The goal is to label. Then there are constraints between a clause C and a variable xi which appears in that clause. And the constraint is simply consistency. Whatever label you want to give to the clause, you must assign the same value to xi on the other side. Right? So that's just the consistency check. And that's it. That's the problem. Find a labeling so as to satisfy as many of these edges. Edges are just consistency checks. Satisfy as many as possible. Right? So that's what is called label cover. Now it's clear that since gap 3 sat is NP hard, optimum of this problem. So let's call the instance of this problem some scripted L for label cover. So if there is a satisfying assignment, then you can just take that assignment, get the correct labeling. You satisfy everything. So opt of this instance is 1. Otherwise, if you are not able to satisfy more than some fraction C of the clauses, then any labeling would also fail on some constant fraction. I hope this is clear, right? So this is also at most some C, maybe some other C prime, which is also very close to 1, something like this. So this is thought of as mild hardness result for label cover. Okay. Now what's great about label cover is basically same as the clique. Label cover you can also amplify hardness using the product construction, just like graph products. So you can take this instance of label cover and apply operation called parallel repetition, which is really this product construction, and construct a new instance of label cover in the most natural way possible. So now on one side you will have k tuples of variables, right? So typically a vertex here would look like a sequence of k variables, all possible sequences of k variables. Similarly, on this side, you are going to have all possible sequences of k clauses, C1, C2 up to C sub k. Okay? and what are the assignments? What do you want to assign to a tuple x1 through xk? Right, all the bit string of length k, right? Presumably it should come from some global satisfying assignment to the Boolean formula, right? The same thing on the other side. You want to assign some label from, you can call it 7 to the k. That for each clause there are 7 possibilities, right? And then that's it. You connect if between these two tuples, x1 occurs in C1, x2 occurs in C2, and so forth. All right? And then that's it. This is now new instance of label cover. And you want to satisfy as many constraints as possible. Now, it's clear that if the optimum of the original instance was 1, you can just take that labeling and just repeat that labeling on every coordinate, in a very good old honest fashion. And you are going to conclude that this new game would be L to the k, right? So this optimum is also 1. Okay. However, what is much trickier is to show that if the original game or label cover, its optimum is bounded away from 1, then the optimum of the kth product version of the label cover, it goes down as a function of k. Ideally, it should go down as exponentially in k. Okay. Now, it's true, but it's much harder to prove. As opposed to, for example, clique. Clique is trivial, essentially, to show that the max clique size is multiplies. But this is true. So it does goes down exponentially small in k to the minus omega k. But this is a difficult result, but also extremely important and foundational result. This by Rutgers in mid-90s. All right. So this is what is called label cover. Okay. And if you never heard anything about this research area, and if you want to know one great hardness result, okay, which would also be very useful if you are in this enterprise, then it's label cover. Okay. Everything starts from label cover, pretty much. Though arguably, it looks like a somewhat artificial, what is called unwieldy problem. Okay. But this is how it is. All right. So this is label cover. Now, at some level, you can forget how this instance came from. That these vertices, they were really k tuples of variables and clauses. The assignments were supposed to be assignments to these tuples, this and so on and so forth. And you can just completely abstract out as a labeling problem. So as an abstraction, it's a labeling problem where one side is called set of vertices capital U, set of vertices capital V on the other side. There is a bipartite graph. Let's say this vertex is little u, this vertex is little v. It's a labeling problem. So V is supposed to get assigned labels from some range 1 to capital R. U is supposed to get assigned an integer from, let's say, some range 1 to capital L. And for every constraint uv, there is a constraint saying which pairs of labels are considered acceptable. Okay. Now, there is one. It's actually an important point that in this construction, any label you assign to the arguably the larger side, it uniquely determines what the label here should be, right? And it's called the projection property, and which is always very useful. So each constraint between pair little u, little v is really defined by some map, which maps any label to the larger side to a unique label to the other side. Okay. So this is how the constraints are defined, and then that's it. That's the abstract version of the label cover problem. Find a labeling which satisfies as many of these constraints as possible. And at this level of abstraction, this was introduced by Arora, Babai, Stern, and Swedick. Right. So that's label cover. Now let's do this sort of bullet point, a direct reduction from label cover. And perhaps maybe the most natural example is you can reduce this and get hardness result for set cover, okay, which is already quite strong. So you won't immediately get natural log of n, but if you are happy with up to constant factors, some log of n, then this would pretty immediately would give it. Okay, and let me even try to quickly sketch it. So what you would do is so these are label cover vertices, little u and little v. I sort of blew up each vertex into a blob. Okay, and let me inside each blob, I will note down the labels which are supposed to be assigned, candidate labels. So 1 up to capital L, and on this side 1 up to capital R. Okay, and then presumably these labels determine these labels. So for example, maybe if you intend to assign label 1 here, on this side it can only be 1 or 2. If you want to assign 2 here, on this side it can only be 3 and 4, so on and so forth. Okay? So something like this. So this is how some sort of pictorial or visual representation of the instance. And now from here, you reduce it to set cover. Of course, I mean, there are more vertices. So what you do is, for each edge, you introduce a universe of elements, right? Call it scripted S, right? So S is some universe of elements. So recall, we are trying to get a reduction from this to set cover. So set cover is a problem about elements and sets. So I'm telling you what the elements are, elements of the universe. So there is going to be one universe, completely separate one, for each edge of the label cover. Okay? Now, if you fix an edge, let's call the universe scripted S. Universe for the edge little u, little v. And so what's the intention? So somehow the intention is you want to mimic the constraint that if you intend to assign label number 2 here, on this side you should be assigning label 3 or 4, right? So the intention is to capture this or mimic this condition in terms of set cover, okay? And I think even in hindsight, I think it's a very natural construction. So you take some universe and construct a collection of sets with the property that, and these come in pairs, that the set is partitioned into 2 pieces called A1, B1. So that's one partition. So this is the universe scripted S. So maybe it's something like this, A1, B1, right? But there could also be another partition called A2, B2. Maybe it could presumably look like this. It's like cutting the universe into 2 pieces, right? So you're taking different cuts, right? And in L possible ways, this capital L being the same capital L here, the number of labels, okay? And with the property that, of course, in each pair, their union is the whole thing, okay? However, if you try to cheat somehow by picking few sets from this side, the AIs, and few sets from BIs, but none of them is actually matching, then the universe will not be covered, okay? So for example, you could try taking 10 sets from one side, A1 through A10, but some different 10 sets from the B side, meaning let's say B11 up to B20. Okay, so suppose you take, now you are even allowed to take, instead of a pair, 10 from each side. It's just that they are not matching. None of the pairs is matching. Then in that case, even if you take their entire union, it still will not cover the universe. Okay? And you can construct such set systems. It's not, just take it as a homework problem, to be solved in 5 minutes after the lecture. You can easily do this. And then that's it. You use this as a gadget. And these L labels, then they correspond to the sets A1 up to AL, right? On the other side, these labels, they correspond to the sets B1 up to B sub L. Okay? And the matching amounts to taking the matching pair of sets. And then that's pretty much really the construction. If you want to do even more, what you actually do is, of course, this vertex U is involved in more edges in the whole label cover, in which case you want to construct a set, which is, let's say, you could construct a set, let's say T for a vertex U of the label cover and the label number 2 of the, right? So this would be the set corresponding to this. This would be really, I mean, this should correspond to the set A2, right? A2. But then you take union of this over all edges in which the vertex U participates in the label cover instance. So, right, so this union over all V which are neighbors of U in the label cover instance, right? And this particular set, it's called A2, but it's specific to that edge. So if you could superscript by that edge just to indicate that dependence, okay? And then that's it. In fact, I already wrote down the entire reduction. And it would be a 10-minute homework problem just to show that this actually reduction works. You know, it's complete, it's sound, provided you are willing to assume that the label cover instance is hard, which it is. Okay? And then that's it. This already gives you log n hardness for set cover. You can do something more sophisticated and in fact get 1 minus epsilon ln n. So this was done. This reduction is what is called Lundiano-Kakis reduction, and the more sophisticated version is the phi-K. Okay, so that takes care of set cover. There are more impressive results. You can do just as a reduction from label cover. For example, you could do optimal result for what is called group Steiner tree. The interesting thing when this result came about was it showed that for this problem, the correct hardness threshold is something like log squared n, which is an interesting threshold in its own right. There is no other problem where you actually get log squared. You could also do undirected edge disjoint paths. So the easy reduction that I gave right in the beginning, that was for the directed edge disjoint paths. It's much more difficult to do it for undirected edge disjoint paths. But this has been done with great success by very nice works by Andrews, Jang, Chuzoy, Khanna. There's also Guruswamy, Talwar. And these results work even when, in the no case of the reduction, you don't even demand that the paths are completely disjoint. You even allow some bounded amount of congestion for each edge. And even then, the problem is hard. Now, when I was actually preparing the lecture, something I had completely forgotten, but I saw it when I was reading these papers, is that indeed these are reductions from label cover directly. However, they already give strong results, but to get the strongest of the results, I think they are even nearly optimal. Actually, they use reductions from some hardness result for CSPs, which Johan Hastad had proved earlier. So I think even for this, it actually eventually it has to go through this main route. This one I call main route because that's where I mostly worked on, right? Okay, so we do have some 14 minutes. I will tell you what this whole business about dictatorship test is. So think of this dictatorship test as a gadget. For me, I don't like the word gadget in this context because somehow when we say gadget, there is something about the word, which has some connotation that it's some, cool object, but nothing particularly deep, some clever object, but not like super deep. On the other hand, when you start analyzing this so-called dictatorship tests, you do really, get slowly, gradually, and progressively, deeper and deeper into issues about analysis, geometry, additive combinatorics, all kinds of quite sophisticated stuff. So what's a dictatorship test? But let's say, fine, saying that it's a gadget at the end of the day. So the intention is the following. You want to build something on top of label cover, right? Now label cover is a labeling problem. So there is a vertex called V in the label cover instance, and this is supposed to get a label from integers 1 up to R, right? And I'm trying to, let's say, reduce label cover to 3-sat. And let's say my goal is to show that 3-sat is 7/8 plus epsilon hard. Okay? And right now I'm just trying to build a gadget. So the label cover is a labeling problem. So there is some vertex V which is supposed to get a label from range 1 through R. And since it's a reduction to 3-sat, somehow this needs to be simulated using variables and clauses, right? Because that's all I have when I come to 3-sat. So you construct variables and clauses as follows. The variables, these correspond to all Boolean strings of length R. Okay, that dimension capital R is the same as the number of labels for label cover. Okay, when you see it for the first time, it's going to sound rather strange. Okay, but this is how it is, right? So there are 2 to the R variables, and what are the clauses? There are going to be 7 to the R clauses constructed as follows. Take any 3 variables. Each variable is a string of length R, right? So pick 3 variables, call them x, y, z, with the property that on each coordinate, there are R coordinates, right? Such that on each coordinate, the bits xi, yi, zi, they satisfy the clause. XOR or yi or zi equals 1 for all I. Does that make sense? Right? So if you want to think of it as a matrix, it's a 3-R matrix where every column has 7 possibilities. So there are 7 to the R such matrices. And each such matrix defines a clause called XOR y or z. Right? So introduce the clause which is called XOR y or z. And that's it. That's the gadget. It's variables and clauses. Right? And now, as ought to be the case with reductions, somehow your intention to assign a label from 1 through R to this vertex V, somehow it has to translate into assignments to these variables which either satisfy all clauses or satisfy only 7/8, right? Makes sense? So now it just actually matter of analysis and Boolean function analysis, as would become immediately clear. So in the yes case of the reduction, so to speak, so suppose your intention was to assign this variable I a label called I being an integer from 1 through R, whatever it may be. Okay? Then here is an assignment to the variables which is going to satisfy all constraints, all clauses. Now, what's an assignment to the variables? It's just a function from 0, 1 to the n to 0, 1. And now we are clearly in the domain of Boolean functions because this set is the variables. So assignments are simply Boolean functions. This dimension should be R. Okay? And we are going to look at this particular function, what is called a dictatorship function. F of any input x is the specific ith coordinate, whichever was your intention to assign label number I to the vertex V. Okay? So suppose I do this. So it's an assignment. Is it clear that it satisfies all clauses? Yeah, I hope so, because by definition, I introduced a clause only when the triple xi via zi satisfied the OR condition, right? So if I assign for each f of x, f of y, f of z to be xi via zi, then it automatically satisfies the clause, right? So it's a specific assignment or a Boolean function which does satisfy all the clauses, right? And these are called dictatorship functions. These are functions which are purely determined by value of one single specific coordinate, right? It's like a dictator, in charge of the entire policy, a single dictator, right? So that's the reason for the name. On the other hand, as is the case with NP hardness reductions, you also want to prove some sort of converse, right? And you can prove the converse. What you can show is the following, that take any assignment, which again is just a Boolean function, any Boolean function which satisfies more than 7/8 plus epsilon fraction of these clauses, okay, must necessarily correspond to some choice of a coordinate between 1 to r. Okay? But this statement is not as I guess clean as you would want. Okay? It needs to be phrased properly in Fourier analytic terminology. So what you can show, roughly speaking, that any Boolean function f, which is an assignment which satisfies more than 7/8 fraction of the clauses, the function f has what is referred to as influential coordinate, right, which is some loosening of the notion of dictator. A dictatorship coordinate is a coordinate which is completely influential, okay? Whereas influential coordinate would be some watering down of this, that there is some coordinate which is reasonably influential. Okay? It can be made precise, it's not such a big deal. And then that's it. These are the properties of the gadgets, and then you somehow combine this gadget with the outer label cover instance. And that's your reduction to 3 sat, which gives 7/8 plus epsilon. Okay? Yeah, I guess we are almost out of time, so maybe I will just tell you maybe here what all we can, what are the kind of things we can get using this framework. So think of this as a framework which can be applied many times over. Okay? It all amounts to constructing gadgets of this type and doing analysis of this kind, which you can imagine is going to be some Fourier analysis. Okay? It's just that the more sophisticated your gadgets get, the more sophisticated analysis you need. And in fact, this is quite amazing. It sort of started with the result. So these are all results of Johann Hastad. Johann Hastad and the whole notion of dictatorship test. This was introduced by a paper. It's called Bellare Goldreich Sudan, the BGS. So it's basically BGS and Hastad, the framework. And then within this framework, in the initial years, the Fourier analysis was sort of elementary, arguably speaking. Though, of course, as you very well know, elementary does not mean easy. Okay? It was still difficult, but elementary. On the other hand, as the years went by, it became more and more, I guess, sophisticated. And at some point, in fact, we as a community, which is the hardness of approximation community, we started inventing new theorems in Fourier analysis, just so that we could use for our reductions. And then they were very interesting theorems on their own right. So I will quote one of them if you haven't heard about this. But in any case, so as we already said, for 3 sat, you can obtain 7/8 plus epsilon using this methodology. Turns out you can also get actually for n to the 1 minus epsilon for clique using this methodology. Now, clique is not a CSP or a constraint satisfaction problem. This whole methodology is tailored for CSPs. Okay? However, it turns out you can prove a certain result for CSPs which then, not in a difficult fashion, implies this n to the 1 minus epsilon for clique. Okay? Now, what's that CSP? So what you can show is the following. So consider a CSP where it's a CSP, right? So it's a variables and constraints. So it's a constraint of arity k plus k choose 2. Think of k as, let's say, 4. So it will be 4 plus, I guess, 6. Okay? Where there are first k variables, they are spatial, x1 through xk, and then k choose 2 is all pairs. And then there are variables which are formally labeled as xij's for all ij's. And a constraint like this is satisfied if xij equals xi or xor xj for all ij. This is just the type of the constraints. Okay? And using this framework, you can prove optimal result for this CSP, and then that implies result for the clique. This was done. The Hastad's original proof was elementary, but extremely difficult. This proof is clean, and this one is by Sudan Trevisan and Samordansky Trevisan. Luca Trevisan. God bless his soul. So you can do this for clique. What else? Yeah, so I guess maybe I will more or less. We still have a couple of minutes, so I could just make some comments. So I guess we did take care of 3-sat clique set cover. You can essentially use this framework to also do vertex cover, max cut, max acyclic subgraph, except that the result for label cover, which we quoted, in some sense, it's not good enough for this. Now, if you remember this picture here, I said that it's a label cover instance where, at least in this picture, it seems like a label on this side has 2 possible labels on this side. Or if you try to view from this side, then this map is 2 to 1. Okay? Actually, in reality, this is not the case. In reality, these maps are many, many to 1. Okay? On the other hand, if you insist on 2 to 1 map, it wasn't clear until very recently whether such label cover instances would be hard, NP hard. But this we did manage to do in 2018. And that's what is referred to as 2 to 2 games conjecture or a theorem. You could try to push it harder and say, what if I want this map to, in fact, 1 to 1, like a perfect matching? And then that would be the unique games conjecture. That would still be open. But under that, you can do vertex cover, max cut, many, many others. I wrote max acyclic subgraph here for a reason, because I hope you recall the definition, right? So it's not a CSP. It's an ordering problem. But somehow, I think this is a paper of Guruswamy, Manokaran, and Prasad Raghavendra, where somehow they managed to massage it and recast it as a CSP somehow. And then it's just a CSP. Okay? So this is a result of Oded Regev and myself. This one is called KKMO, myself, Guy Kindler, Mossel, and O'Donnell. And I did promise that I will tell you a new Fourier analytic result which we had to prove. And that's exactly for this max cut result. So we conjectured it on our original paper, and then it was actually proved by Mossel, O'Donnell, and Oleshkevitz. So what this result said is that given any Boolean function, so the result is known as majority is stablest. And as the name indicates, majority is the stablest function. That's roughly the result. But you have to make it precise for it to be meaningful. So the result is that among all Boolean functions, 0, 1 to the n to 0, 1, they need to be non-trivial functions, meaning it cannot be just constant 0 or constant 1. So let's say the expectation of this function is 1/2. So it's a perfectly balanced function. And it cannot have influential coordinates. So if you recall what this influential coordinate business was, it was supposed to be some kind of opposite or a counterpoint to the dictatorship functions. So in some sense, functions which do not have influential coordinates, they are sort of functions which are far from being dictators, right? So think of democracies, okay? So your function has to be democracy, okay? So, so if you have a function which is, let's say, balanced and it's a democracy, then among such functions, majority is the function which is most noise stable. It's clear what noise stable should mean, that if I flip the value of each coordinate by some small probability, then the value of the function itself should not change by too much probability. Right? So, yeah, so then that's it. Yeah, so I'll stop here.
Any questions?
Yeah.
So if we're thinking about using like the sparsification lemma, so if we look at like 3-sat,
Yeah.
7/8 plus an epsilon approximations, does that translate well? So if we break the 3-sat formula into some, I don't know, sub-exponential number of these, like a disjunction of these sparse formula, what can we say about being able to, like the hardness of approximation if we have, I guess, sparse formulas?
So I suppose by sparse formulas you mean, let's say, the number of clauses is linear in the number of variables. So in fact, all these reductions have the property that the hard instances that they produce, they are already sparse.
Oh, that's true. Okay.
Yeah.
They're already, okay, so already we have this linear relationship.
Yeah, the number of clauses is linear in the number of variables.
And so what can we say about the approximation hardness under ETH, say?
The ETH is, that's a completely different assumption. Meaning you cannot solve 3-sat in 2 to the epsilon n time. That's in some sense incompatible assumption.
Thank you.
My question can also be a little personal, as you are the person who proposed unique games conjecture. Before you propose it formally and publish it, did you have an insight that it can have a great role in approximability theory, or no? You just published it later, people understood, oh, it has a lot of applications.
Yeah, it was much more of the second thing. I mean, it's difficult to see, in the beginning, significance of things. Yeah, as I often like to say, hindsight. The wisdom is always gained in hindsight. You always start proving result. Not always, but very often. Just prove the result by hook or crook, okay, and then discover the intuition later. I'm being a bit exaggerated, but.
Comments about what's a framework for proving hardness for sparse cut right now?
There is no framework. So for example, those which are in the open bracket, in particular, let's say TSP and sparsest cut, we know nothing, not even an approach. Though for sparsest cut, you can get something if you assume a version of the unique games conjecture which is even stronger, which was made by Raghavendra and Steurer, which is called the small set expansion conjecture. So then if you assume that, then you get hardness results for sparsest cut, almost, I guess, nearly automatically.
So for the undirected execution path, does that result relate to graph products in that directed case? Or
no, I don't think so. You can't just get it by graph products. However, I guess those results about edge disjoint paths, I'm not an expert on that, so I cannot say with complete confidence. But as far as I can recall, these things you can't just get by some product construction.
So you're saying like it's we have a framework of label cover.
They do start from label cover, or at least So the results for edge disjoint paths, you can classify them into strong results, which were already very impressive, and then even more impressive near optimal results, which came later. The initial results were, as far as I remember, they were just reductions directly from label cover. And then the near optimal ones, they are reductions from, really from a CSP, which actually essentially the same as this CSP, which is used for the click.
You comment on the mapping between techniques and the picture, so I guess Boolean functionality goes into the...
Yeah, so I guess all Boolean function analysis is in this main thread. It really starts at the dictatorship test and below. And
About the geometry, like where that...
the geometry also is in the same thing because, for example, the majority is stabilist. It's a Boolean analysis statement, but the way it is proved, it is by mapping the theorem that you want to prove into a statement about isoperimetry in the real Gaussian space, and answer an isoperimetric question in the real Gaussian space, which was already known before in pure mathematics.
Thanks, Subhash, again.
Oh.